Hi, welcome. This is the 17th session on measure theory. I hope I got my numbers correct. And fourth in the section on sequences of measurable functions. Today, we are going to talk about the real building blocks of integration theory, the so-called simple functions. So this is simple functions 1, but in measurable functions, it may be the 5th one. And in all measure theory, 17th one. Keep track of some numbers. How does it matter? Okay, let's get started. So recall that we have if a function a b to r, okay, and what is meant by step function? Step function means that a b is partitioned into various intervals of this kind. Okay, in each one of them it will be constant c0, c1, and this may be cn minus 1. Okay, this is my x0 equal to a and x1, and this x2, this xn minus 1, xn equal to b. So in each of the things, f is constant ci on where xi2, xi plus 1, and I is less than or equal to n minus 1. I hope I got it correct. Anyway, okay, this is called a step function, right? So we want to look for analogues. Let me see whether I started a screen share and sorting. Real paranoid. Okay. So suppose I have a measurable space. Okay. Measurable space. I want to define a simple function. A simple function, by definition, is a function xb to r, not extended derivatives. Okay. Not r. Okay. There are some authors who allow simple function to take infinite values, but I don't. Okay, a simple function which is measurable. First condition is measurable, and second condition is it takes only finitely many values. Okay, so let's look at this is my x, and okay, these are my things. Suppose the values, let the values be c1 to cn, and this is c1, this is e1, this is e2, corresponding to c2 and c1. What does it mean? If I define ei to be f inverse of singleton ci, okay, this will be a measurable set. I have not said it, but it's very easy. If f is any measurable function, an aside, if f is any measurable function xb to r or re, okay, and if c is in r, then f equal to c is a measurable set. Okay, this is measurable. Why? That's because this is intersection of f greater than or equal to c and intersection of f less than or equal to c. We know the by definition of measurability, these are all measurable sets. Okay. So this is a very often used corollary, but as usual, the textbooks will always give the converse is not true. That means there exists a function xb to r, so that for every c in r or re, f inverse of singleton c is measurable, but f is not. Okay, this one uses the existence of non-measurable set to construct such a thing. I could have given when I did non-measurable set, I forgot. Okay, but let's not worry about it at present. So let's come back to our main problem on hand. So if f is a simple function, that is Let me change the color. If f of x is C1 to Cn, which is a subset of R, so if I define EI to be f inverse of singleton Ci, usually one writes it as f inverse of Ci itself. Okay, for 1 less than or equal to I less than or equal to n, these are measurable sets, right? And notice that this is a partition. It's a measurable partition. What does it mean? It is a partition in the usual sense, and each of the partitioning subsets is a measurable set. Yeah, because E1 intersection E2, if x belong to that, fx must be C1, also fx must be C2, but these are all the values. Okay, this is a set I wrote, therefore these were also distinct. Okay, so let us see. Yeah, I'm assuming C1 to Cn are the distinct values. This is just to be on pedantic side. I just want to say that. Okay. Yeah, I think I have to switch on my fan. Just 1 sec. Okay. So let us look at some examples. The description, whatever I did, already gives me something very interesting. Start with any subset E of X, okay, and let's look at E complement, right? Call this as A and B. Then if I look at alpha times integrator function of A plus beta times integrator function of B, okay, this will be a simple function. Of course, I am assuming E is measurable, right? Why? Because what are the values it takes? It takes only two values, alpha and beta. Remember, these are disjoint. Therefore, this is. Have you understood this? So, pause, review, proceed. Okay. Second example, if suppose A and B are measurable sets, okay, then also indicator function of A plus indicator function of B, okay, this will be a simple function. Why? Again, notice that, again, let me draw a picture. So this is my A and this is my B. Right? So now what are the values it takes? See, for example, if I take here points in A minus B, on A minus B, if x belong to that, call this as F, then fx will be 1. If x belong to B minus A, my fx will be 1. But if x belong to A intersection B, then, sorry, this is alpha, this is beta. Okay, this will be alpha plus beta. Do you understand this? Therefore, there are 3 values. It takes only 3 values, right? So, for example, yeah, therefore f takes only 3 values: alpha, beta, and alpha plus beta. And what is the corresponding measurable partition? That is A minus B, A intersection B, and B minus A. Right? So if you want, I can put a different color for this. So this is your A intersection B. Okay? Right. So more generally, let AK belong to B, 1 less than or equal to K less than or equal to N, and CK belong to R, define if F to be summation CK into indicator function of AK, K equal to 1 to N. Okay, this will be a simple function. Because what are all the possible values? Possible values will be summation Ck, K running over J, okay, where J is a subset of 1 to N. Right? And what is the measurable? You follow that? These are all the possible values. Also, 0 may be a possible value, because if x is not in the union of a k equal to 1 to n, then fx is 0. Right? So what are all the possible values will be? 0 summation ck running over j, where j is a subset of 1 to n. If j is empty set, I can interpret as 0. The sum is 0. In that case, I don't know to write it. Is that clear? Pause, review, proceed. These are the possible values. Notice that not all of them may occur. For example, C1 plus C2 plus C3. If it occurs, what does it mean? A1 intersection A2 intersection A3 should be non-empty. It may or may not happen. Okay, only if it's non-empty, this will be a value. Right? So this is only possible values, not all the. I am not claiming these are all the values. Okay. Pause, review, proceed. Okay. So there are two ways of looking at simple functions. Notice that all our simple functions by definition are measurable, so I don't use the word measurable simple function. Okay, I don't use that. Simple function by definition for me is measurable. And second, it is a real value. It does not take infinite value in the extended real number system. It does not take infinite values. Okay. One is, okay, it takes only finitely many values. And two, that it is a finite linear combination of integer functions. Functions of measurable sets. Okay. So I want to prove 2 is also a simple function. Functions of the kind 2, type 2 functions are also simple. How do I prove that? As I said, finite linear combination of simple functions, they take only finite many values, right? So let us do that. Okay, suppose my f is summation ck indicator function of ak, k equal to 1 to n. Of course, ak's are measurable. Okay. Now I know f takes only finitely many values. Okay, let them be alpha 1 to alpha m. Okay, that is, these are the distinct values assumed by f. Okay, right? Then I want to define the following. Let us look at my function g. Okay, let me define. Let ek by definition be equal to f inverse of alpha k less than or equal to 1 less than or equal to m. Then I know these are all measurable. And on each ek, the value of f is alpha k. Therefore, I define this function alpha k and indicator function of k k equal to 1 to m. Yeah, you understand this? Right. So this is a simple function. And what is the partition? Measurable partition. Okay. Now notice that, as I said, it's a simple function. So outside, if x is in capital X minus union of k equal to 1 to n, then fx is by definition 0. Right? So my alpha will also be 0. Therefore, measurable partition is exactly E1 to E2. I am using the same k. Perhaps I should have used here as I equal to 1 to n, here k equal to 1 to m, but I think all of us are smart, we understand what it means. So this is the measurable partition. Okay, so let us recall. Okay, after the definition, teacher quickly goes to the next major result, what we are looking at, trying to understand. Okay, so whenever you try to understand something in depth and better, there is a possibility you will get confused. It may be intimidating. But then once you overcome, understand, you will feel more confident. Okay. So bear with me. You are going to become confident. Okay, let us do that. Right. So let us try to do this. What I want to do, yeah, I put that. Yeah, right. Okay. So if f is any simple function, see, notice that, let me just give an example of a simple function. If I write characteristic function of 0, 1, this is a simple function because it takes only values 0 and 1. But I can also write it as I of q plus I of 0, 1 minus q. That is indicator function of this. It's the same function. Do you see that? These are the same. Are you following? Or I can also write it as I of 0 t and plus the indicator function of t to 1 for any t. You can even I can make it equality, but let me assume. So the first point I want to take, notice that again all these functions take only two values and all the functions are the same. So what I am trying to say is, given a simple function with the values, distinct values, alpha 1 to alpha n, okay, and defining ei to be f inverse of alpha I, these are measurable, right? Then f is same as alpha I indicated function I of ei, I equal to 1 to n. This is called the standard representation. Notice that this is a very unique. There is no source of confusion. For example, let us look at what we did earlier. F of my f was this I times b. Its standard representation is going to be I of a minus b plus I of a intersection b. When I say I, it's indicator function. B minus a plus indicator function of x minus union a union b. This is 0. Right? This is one time this. For example, if I take this to be alpha and beta, this will be alpha, this will be alpha plus beta is the coefficient, this will be beta, the coefficient here is 0. Do you understand that? My f function is f alpha times indicator function of a plus beta times indicator function of b. Then the standard representation is alpha indicator function of a minus b plus beta indicator function of b minus a plus alpha plus beta indicator function of a intersection b plus 0 times indicator function of the set x minus a union b. This is the standard representation. Okay, pause, review, proceed. So in a typical classroom, okay, the teacher defines simple function. Immediately he proves the standard representation. By definition it's easy. And after that he goes to the theorem. What we took about 15-20 minutes, usually let's spend less than a minute or maximum 2 minutes. Alright. But this way of looking at, but this is a kind of trick which I always do. Whenever I learn a new concept, okay, I don't keep reading. I just stop and try to understand it, asking a lot of such questions and trying to explore, worry. I may or may not get the answer, but I always try. Okay, so that I become very confident what I'm talking about. Okay, I become comfortable to work with them also. It's like getting to know a friend. Just being introduced with a name and designation is not going to. But the more I talk to him, the more I okay converse with him, I become more friendly. So I understand that person well. The same way. Okay, I hope you don't get bored with this kind of thing. Huh? You want serious mathematics? Let's go. Right. Now I want to ask you a question. Suppose f from xb to r is a measurable function. Assume f is greater than 0. That is, f takes values in 0 to infinity. Right? I want to know the existence of a simple function. I always write denoted by s, okay, so that 0 is less than or equal to s, less than or equal to f. Is on x. So what does it mean? For every x in capital S, s of x should be less than or equal to fx. You understand that? I want to know that there is a simple function. Right. The answer is easy. What do you do, since I said f takes values, f of x is 0 for all x, in x is going to be union of f greater than 1 by n in n. Do you understand this? This is by Archimedean property. Because if fx is greater than 0, okay, there is an n such that n times fx is greater than 1 and hence fx is greater than 1 by n. Right? Therefore, this must happen. Right? Now let's, of course, as usual, let's remember one of my conditions, the mu of x. Right. Okay. See, now this is how I learned things. Okay. So this question I am not addressing on any measurable space, but on a measure space. X b mu. Okay. Right. You see that? That's a fun. Okay. So now remember, by definition mu of x, we always assume mu x is not 0. It's not trivial. Okay. Therefore, this is a union and this is mu of x is therefore positive. Right? Therefore, there exists at least one n so that the set f greater than 1 by n, its measure must be positive. Because if for otherwise, what is the thing? For every n, mu of f greater than 1 by n is measure 0. Therefore, it's a countable linear measurable sets. We know then x is also measure 0. That's a contradiction. Right? Therefore, there exists called this set as En. En to be this set. F greater than 1 by n. Okay, then mu of E is greater than 0. Right? Therefore, if I look at my S to be 1 by n times indicator function of En, then 0 is less than or equal to S, and that's less than or equal to F. Is that correct? Yeah, that's not correct. Yeah, the only thing I know is unanswered. Is that correct? Because now let's look at my ENs are increasing. Think of this as X. Okay, this is my E1, this is my E2, this is my E3, and so on. They are increasing, right? Now if you give X in En, said that, okay, if my X is not in En, then it will be 0. Therefore S of X will be 0, where it will be 1 by n. Do you understand that? I want you to understand this. For X in En, this is correct. Okay, this will be S of X will be 1 by n. It's greater than 1 by n, and this is greater than that. Okay, this is a correct statement. Yeah, if X is in En, then S of X is 1 by n. Okay, but that's less than F of X. Therefore it's correct. Right? Suppose X is not in En. Right? Then S of X is 0. Right? Therefore, again, this is a correct statement because S of X is less than or equal to Fx because Fx is non-negative. Okay? Right. So pause, review, proceed. So I'm just thinking of some examples so that I become very confident. Okay, some of the things you can see, I'm just thinking aloud so that you can see. I make some small mistakes that then I recover. Yeah, for example, when I want to define this, I thought any measurable space, then I found it has to be measure space. Yeah, measure must be needed to prove that statement. Okay, that's fun. Right. Okay. Now let's go to the next one. Of course, without that also one can prove perhaps. Okay, it's hindsight I can think, but let's not worry about such things. Okay. Now, next important result, this is the crucial result about simple functions. This is what is needed to define integration. So let us let's look at that. So this is the theorem. Let f from xb to r be non-negative and measurable. Yeah, I'm sorry, let's go back to this. I don't really require measure here because if you define En to be union of f greater than 1 by n, right, then the En increases to x, right? Are you following? So fix one such n, therefore there exists an n such that En is not empty, right? So if you define S to be 1 by n times indicator function of that En, then that S will satisfy our property. So I don't really require measure. Okay, not required. Okay. Then there exists a sequence of simple functions Sn. Okay, so that one, Sn's are non-negative, and two, Sn increases to f pointwise. So in particular, you can see this Sn has to be like this, right? So we don't need. So if I have remembered this theorem well, I should already have foreseen the mu is not required for this result. Do you understand? I always go back and forth to think. Okay? Right. Is that all right? This is a statement. Now let's try to understand. I will first define the basic idea of the proof, or what you call strategy. What we do is I look at first a simple example, and let us say my x is 0 to infinity, or r also. Let us look at the function f(x) equal to x, identity function, right? Then what you do is you truncate this function at various levels. This is at 1 you truncate, okay? At 2 you truncate, at 3 you truncate, and so on, right? Go slow, don't get worked up with it. So what I want to do is at each level, this r or this is rather 0 infinity, I want to look at this one. The first stage I am splitting as 0 1 union 1 infinity, okay? And 0 1 I split it, bisect it, that is 0 half union half 1. Maybe if you want, make it 0 1 and include 1 to infinity, right? Then what do I do? Okay. Now let's look at this. Here, this is my half, right? So let us look at the set of points x in capital X, okay? Yeah, so that fx is less than or equal to half, less than half, right? Then I define the value at those points to be 0. This maybe this is my half, okay? And here it half. After this, what happens? It's 1. So I'm sorry, I should have removed this, okay? And in this interval, what I do is 1, okay? Here I define it to be half, okay? And if my fx, okay, this is my set x, so call this, okay? On this set I define it to be, let us call this e, whatever it is, okay? Let me at present write it a. And this I define my simple function s1 to be 0 and s1 to be half on this set x in x, so that half less than or equal to fx less than 1. I define my s1 to be half, and the leftover thing will be x in x, so that fx is greater than or equal to 1. I define s1 to be 1. Therefore the picture will be, so my picture for s1 will look like this. The graph of s1, I am just writing this. This is my half, this is my 1, and it goes on, right? So here the function is this 0, here it is half, and after this is 1. 0, half, 1. Okay. So notice that what I have done. So let x be, and f is a simple function. So what I define is, I define my s1 to be 0 on the set x. Let me write 0 less than or equal to f less than half, and equal to half on half less than or equal to f less than 1, and on f greater than or equal to 1. That is, I just put a slab. After this is the value. You understood this? Now, how do I define S2? Please pause, review, proceed. Most often the teachers write the formula for Sn, and they say it's very easy to check Sn increases. These are all simple functions, etc. and typically in textbooks will give 4-line proof. But it takes there's a lot of geometry, and once you go through the details, you will see how we are actually approximating. Okay, this is the usual exhaustion method of integration theory, so you should learn this well. Okay, are you happy with S1? Now when I want to do S2, what I do is, for S1 I truncate it. Okay, anything above y equal to 1 I cut it. All will take values 1. Now what I do is I increase 1 to 2. I truncate it to 2, but then I do something more, because everybody in 0 to half were assigned only 0. It may be something like even 1/4. They are also assigned 0. Right? So what I do is, now I bisect each of the previous intervals also. Okay? Go through it. Let's go slowly. You will understand this proof. Hi. After explaining the idea how to go to the second step, next 10 to 15 minutes I was lecturing without screen sharing. So I completed almost the proof of the theorem, okay, without screen sharing. So I had to delete it and re-record. Okay, so these are the kind of mistakes one has to do and learn. So it's somewhat time consuming. Anyway, I hope this time I will not do that. Let us go ahead. See, you can see that I have done all those things. Now I have to do it again. Okay, let's do it. So second stage, what we want to do is, I have 0, 1 and 0, 2, right? I already split it into half. Okay, what I will do is, I will again split it into, bisect it. Therefore, this is going to be 0 upon 2 squared, 1 upon 2 squared, 2 upon 2 squared, and 3 upon 2 squared, and 4 upon 2 squared. That is 2 squared, right? And this again is split into 4 parts. Therefore, this will be 5 upon 2 squared, 6, okay, and 6 upon 2 squared, and 7 upon 2 squared, and 8 upon 2 squared. Right? You follow that? So now I am going to define my S2 like this. S2 by definition is going to be, in each of the interval, what I will do is start with x, okay, and suppose fx takes values between 0 and half, right? Then fx has to lie in exactly one of them. Remember, these are all partitioning. Right? So my fx, let me assume less than 2, it has to be exactly in one of them, right? Then what I will do, suppose my fx is here, I define S2 of x to be the left-hand endpoint of the unique interval, right? That is, I am going to define it is k by 2 squared, where if, okay, my fx lies in k by 2 squared into k plus 1 by 2 squared. That is the left-hand endpoint. Remember this as the left-hand endpoint of this. Is that clear to all? Yeah. So here, for example, if my fx lies here, it will be 0. If fx lies here, it will be 1 by 2 squared. If fx lies here, it will be 5 by 2 squared. If my fx lies here, it will be 7 by 2 squared. Okay. And equal to 2 if my fx is greater than or equal to 2. So the picture, okay, for this, let us look at the picture for our function fx equal to ax and 0 infinity. Okay, then my S2 will look like this. Let us say this is 1, this is 1/4, this is 2/4, this is 3/4, 5/4, 6/4, 7/4, and 8/4, right? So here this will be like this. So I will use a different color on this. This will be this, right? This is my original function. The original function is this. fx equal to x function. Okay, so here this is the value, and here on this the value will be only half. Okay, on this the value will be 1. On this the value, let me just extend it. On this the value will be 7/8. That's it. You see that earlier what was the value? Earlier it was 0 all through. Earlier it was 0 all through, and here it was only half of through. Okay, whereas now we have improved. Here it is going to be 3/4, for example. Are you following? Here 3/4, it will be 3/4, and this will be half, and so on. So we can see that we are improving. So in general, so at the nth stage, okay, my 0 to infinity, okay, is going to be split into union of j and k, union n to infinity, where j and k, okay, how many things at each level? What I am going to do is, see, I am just increasing the slab truncation, okay, at n equal to 2, we truncated at a 2. Everybody, the maximum of my S2 was always less than or equal to 2, and Sn always less than or equal to n. So we increase the truncation from n to n plus 1, and also at the each of the time the area subintervals are again bisected, right? Okay, so nth stage, this is my j and k. What is my j and k? J and k is the kth subinterval at the nth stage. So what is that? It is nothing other than k by, in all, how many intervals are there? Notice that at each level, nth stage, okay, I had only 0, 1 and 2 power 1, n equal to 1. N equal to 2, I have 0 to 2. Okay, and how many intervals I had? 2 into 2 square, because this also I split into 4, and this also I split into 4, therefore 2 into 2 squared, and so on. Therefore, the nth stage, I am going to have n into 2 power n subintervals, each of length 1 by 2 power n, of 0 n. Okay, so this is 0, this is n, this will be my k minus 1 by 2 power n and k by 2 power n, and my k runs from 1 to n 2 power n intervals. Okay, so my j and k is going to be k minus 1 by 2 power n, k by 2 power n, or let me say k equal to n I want. Yeah, right. Okay, is that clear? So my e and k is f inverse of this, so this is measurable, right? Therefore my 0 infinity, I wanted to increase, maybe I could, yeah, new page after, yeah. So what happened to that? I wrote n, n1, n, etc. Oh, I should have it here. Okay, e and k, and then e n star, which is n to infinity. Therefore, at the nth stage, okay, the value is split into union of j and k equal to 1 to n into 2 power n union j n star, And my En star by definition is F inverse of Jn star. This is also measurable, right? Therefore, my X is split into union of J and K, K equal to 1 to N to 2 power N union En star, right? So what does it mean? This means if this is a measurable partition, it's a finite measurable partition, finite meaning finite number of partitioning subsets. Okay, so in all 1 plus N into 2 to the power N subsets are there. Okay, and this is a partition, and hence if you give me any X, Fx has to be here. Sorry, again E and K. You see, remember J and K is the interval. F inverse of J and K is the measurable subset E and K, the pre-image. Sorry for the mistake. Anyway, so if X is in X, there exists a unique K such that X is in E and K or X is in E and star. If X is not in E and star, then it has to be unique. Okay, and if X, therefore Fx, where does it lie? It lies in J and K. What is J and K? It is K minus 1 by 2 to the power N, K by, sorry, yeah, K by 2 to the power N. Then I define my Sn of X to be the left end point, that is K minus 1 by 2 to the power N if my X lies in J and K are equal to N if X lies in En star, that is if Fx is greater than equal to N. Okay, pause, review, proceed. Therefore, my Sn is going to be my K minus 1 by 2 power N, an integrator function of J and K is running from 1 to N 2 to the power N plus N into integrator function of E and K. Again, I am making the mistake E and K, En star. Okay, notice that Sn is a simple function. Okay, and second, notice that Sn I want to say is less than or equal to Sn plus 1, and also Sn is less than or equal to F. Is that clear? Yes, because as I said, if X is there, okay, what is Sn of X? That lies in J and K if X lies in E and K, sorry, J if X lies in E and K, then Sn of X lies in J and K, which is equal to, sorry, F. So if X lies in E and K, Fx lies in J and K, right? And what is Sn of X? Sn of X is K minus 1 by 2 to the power N, whereas this is K minus 1 by 2 to the power N, K by 2 to the power N. Therefore, Sn of X is less than or equal to Fx for all X and for all N. Okay, pause, review, proceed. So I shall stop it. The main power went off, and my battery is also, laptop battery is also running down. I'll pause it and start again. Hi, or come back. Let's hope that I'll be able to finish it in time. Another 5 minutes. Okay. Let us look at our function, this function, right? Now you can see it is improving again and again. 1, 2, this is 3. You can see this will be 1 by 2 cube, right? 1 by 8. Therefore, it will be 1 by 8. It will be 0, and 2 by 2, 1/4, 3 by 8, 4 by 8, 5 by 8, 6 by 8, 7 by 8. So you can see it keeps improving. This is the value here, this is the value here, this is the value here, and this is the value here, etc. So you can see that keeps improving, right? So what we saw is Sn of x is Sn is less than equal to Fn for all n. Next is Sn of x is less than equal to Sn plus 1 of x for all x. Why? As I explained, okay, now suppose x is in J and k. What is J and k? J and k is k minus 1 by 2 to the power n, k by 2 to the power n, right? Now that interval, what happens to that? So I have k by k minus 1 by 2 power n, k by 2 power n. My fx lies somewhere here. But this interval is again split into half. That is going to be 2 times this fellow by 2 power n plus 1 and 2k minus 2, therefore 2k minus 1 by 2 to the power n plus 1, and this will be 2 power k into 2 to the power n plus 1, right? Therefore my fx may lie here or lie here. If fx lies here, okay, my Sn plus 1 of x will be only this 2 into k minus 1 by 2 to the power n 1, that is same as the earlier one, right? K minus 1 by 2 to the power n. Do you follow that? This fellow is split into two things, 2 into k minus 1 by 2 power n plus 1 and 2k minus 1 by 2 power n plus 1 union 2 power k minus 1 by 2 power n plus 1 and 2k by 2 power n plus 1, right? My fx. So if fx right here, so if fx lies here, then what will be my Sn plus 1 of x? That will be 2k k minus 1 by 2 power n plus 1, which is k minus 1 by 2 power n, which is Sn of x. Whereas if fx lies here, okay, if fx lies here, then Sn plus 1 of x will be 2k minus 1 by 2 power n plus 1. That will be greater than 2k minus 2 by 2 power n plus 1, which is my Sn of x, right? Therefore if my 0 less than equal to fx is less than equal to n, this is what happened, right? Now so my fx, suppose my fx was greater than or equal to n, then Sn of x was n, right? So this is my n, and for n plus 1 I would have started from here, right? Therefore my fx either was here or was here. Are you following? Yes. If fx lies in n to n plus 1, okay, that is split into my j and k's, right? So my Sn plus 1 of x again is greater than equal to Sn of x. If my fx lies here, then my Sn plus 1 of x will be n plus 1. That will be greater than equal to Sn of x, because Sn of x is maximum is n anyway. Are you following? It's exactly the same logic. Yes. So what you have shown is Sn 0 less than equal to Sn less than equal to n, and Sns are increasing. These are all simple functions. Next step is I want to prove Sn increases to Sn of x increases to f of x for all x. Okay, let's assume fx is finite. Okay, x is an R, right? Then notice that my fx, where does it lie? It lies in k minus 1 by 2 to the power n by k by 2 to the power n at any n. My Sn will be here. My fx will be somewhere here, but Sn of x will always be here. Therefore, the distance between fx and Sn minus of x will be less than or equal to 1 by 2 to the power n. Yeah, it's actually strict, but doesn't matter. Are you following? But suppose my fx equal to infinity, right? Then what will happen? My Sn of x is n for all n. Therefore, Sn of x again increases to f of x. Therefore, what you have proved is Sn are simple, they increase to f. Okay. So it's almost, I think, about 50 minutes to 60 minutes. Usually it is done less than 10 minutes in a typical classroom. But you see that it's very easy. Okay. Just because I might have got confused with J and K, E and K, etc. Okay. But if once the concepts are clear, you should not get confused. Watch it again. So understand the geometry. After that, it is much easier. That essence are how essence are defined and how we keep refining. At first, at the nth stage, I cut off. Anybody who is fx and greater than equal to n, they all will be assigned n. And 0 to n, I split it into two, each k to k plus 1 between 0 and n, I split it into 2 to the power n subintervals of equal length. Therefore, in all, 0 to n is split into n into 2 to the power n subintervals. So my fx has to lie there somewhere there. If fx is less than or equal to n, okay, then what do I do is whichever interval it lies, take the left endpoint. I define the simple function defined using that. This is a very, very simple idea, but beautiful. It takes time, but I hope you enjoy once you go through that. Don't try.